Hello everyone, this video covers section 5.3 higher order Taylor methods. That's the title of the section. In the last section or the last video we cover Euler's method. Remember that this is a method to solve initial value problems of this kind. So this is what we're trying to solve, initial value problems that look like this. The goal of this section is to look to new methods to solve these initial value problems. In general, the method we used before, Euler's method, and the one we're going to use right now is technically called a difference method. This is the initial condition. This is the actual method. And tau I plus 1 is what is called the local truncation error. If you recall from section 5.2, when we found Euler's method, all of this was based on Taylor polynomials or Taylor series. Okay. And to refresh your memory, remember this is the Taylor polynomial that we used before. Ti, y of ti plus h of 2 over 2 of y double prime of K I, where K I was between a and b, and h was equals to ti plus 1 minus ti. Remember that for Euler's method, this is technically y prime, and for Euler, this is what we have before. We have the y of ti plus 1 was equals to y of ti plus h f of ti, y of ti. That was the method, and this was the local truncation error. Hence, if wi is almost equals to yti, then the method was the following. W0 was equals to alpha, which is the initial condition, and then wi plus 1 was the same thing as wi plus h f of ti wi. And this is what we call the Euler's method. Notice here the local truncation error in absolute value is less than or equals to h over 2 from here times m, where m is the bound for the second derivative. Or in other words, the second derivative has to be bounded by m. In fact, Euler's method is actually a Taylor's method of order 1. So Euler is a Taylor's method of order 1. Before we proceed, a small correction. This should be ti, and it should be ti plus 1. So make sure you fix this part. Now, in general, a Taylor polynomial will give you this. So this is a general Taylor polynomial. Now notice, and we have used this before, we use this for Euler's method. Notice that y prime of t is just the same thing as f of t yt, so that's in fact the definition of the derivative. Y double prime of t is equals to f prime of t yt. And if we keep going, that means the k derivative is equals to this. Okay, and this is true if K I is between ti plus 1 and ti. Therefore, if you plug all of this in here, we get the following. So from here we'll have y of ti plus 1 should be equals to y of ti plus h of f of ti y of ti plus h squared over 2 f prime ti y of ti and so forth, plus h to the n or n factorial. Okay, and then finally the truncation error, which is this, where we already know that K I is between ti and ti plus 1. So that's true there, and it's true here. All right, let's look to Taylor's method of order n in more detail. This is the difference method right here. Again, this is the initial condition. This is the actual method. Wi plus 1 is equal to Wi plus h, which is the step size, t to the n of ti Wi, where tn is equals to all of this. So depending on which order you want, that's how far along you have to move in the derivatives. All right, so let's do an example. Let's say that we want to solve this differential equation using Taylor's method of order 2. That means that the value for lowercase n is equals to 2. Here we have capital N equals to 10. So that means that the value for h is going to be equals to 0.2. Remember, this was b minus a over n. So that's how we get the 0.2. And the value for ti is equals to a, which is 0 in this case, plus h. So therefore, in this particular example, this is just equals to 0.2i. Before we go any further, recall that this is f of t y. So therefore, f prime, because we're going to need f prime of ty is equals to y prime minus 2t plus 0. But remember that y prime is equals to all of this. So therefore this will be y minus t squared plus 1 minus 2t. Okay, be careful with this step. So again, notice the y prime is equals to all of that, which is exactly the same thing as just y minus t squared plus 1 minus 2t. Since we are applying order 2, all we had to find is t of 2 of ti wi, which in our case, this should be just f of ti wi plus h over 2 f prime of ti wi, which once we simplify for this, we will get wi minus t squared I plus 1, and then plus h over 2, and this is wi minus ti squared plus 1 minus 2 ti. Now, the following simplification is not really necessary, but it will make computing things a lot easier, especially you have to compute things by hand. So you can factor the following, and this will look like this. And you should really check on this. Stop the video and you check you get this. For example, here you have wi and wi. So if you factor that, you end up with this. You have ti squared, and you have the one in here and the one in there, and then you have just this one left. You multiply this times that, it gives you that. Again, this is not 100% necessary, but it will make computing the values easier. If we put everything together, we will get the following difference method. We will have W0 equals to 0.5, which was the initial condition, and then Wi plus 1 will be equals to Wi plus h. Remember, times this should go in here, so this will be 1 plus h over 2 wi minus ti squared plus 1 minus h of ti. Remember the h is equals to 0.2 in this case, and ti is equals to 0.2i, and this is true for I equals to 1, 2, all the way to 10, which is also the case here. I is equals to 1, 2, all the way to 10. So therefore, if we simplify that using this, we end up with wi plus 0.2. This will be 1 plus 0.2 over 2 wi minus 0.04 I squared plus 1 minus 0.04 I. And you should definitely stop the video and check the following. Once you simplify everything, this will give you 1.22 wi minus 0.0088 I squared minus 0.008 I plus 0.22. And again, this is true for I equals to 1, 2, all the way to 10. For example, let's say you want to approximate the values now. So if you wanted to find y of 0.2, this is approximately equals to w1, which it should be equals to 1.2, w0, which is 0.5, minus 0.0088 times 0 square minus 0.008 times 0 plus 0.22, and this is around 0.83. Then you move one more step, and let's say you want to find y of 0.5. This is approximately equals to y w2. So this will be 1.22 times 0.83, because now w1 is this one, minus 0.0088 times 1 minus 0.008 times 1. This should actually be square, but doesn't make any difference. Plus 0.22, and this is equals to 1.2518. As you can see, this is not hard. This is just tedious. It takes a while. That's why you want to program this and let MATLAB do all the work. Again, also it's not necessary to simplify things all the way to here, but as you can see, that makes computing these values a bit easier, because now you only have to put 1, 2, 3, and so forth in here. Now, in general, you will get this. So you compute all the values. This is the values that you end up with. Here are all the values all the way up to I equals to 10. And this is the error. Which is important to notice that the error is actually increasing, not decreasing. You can see that. And just keep in mind that we're only doing order 2. You wanted to do order 4 or 5 or 6, you had to do a lot more computations. And this brings us to the last part of this section, theorem 5.12, which is what we'll see on the next page. Theorem 5.12 says the following: if Taylor's method of order n is used to approximate the solution to the initial value problem with a step size h, and if y has n plus 1 continuous derivatives, then the local truncation error is equals to O of hn. If you notice in the last problem, we only use n equals to 2. So that's why the order of convergence from the previous problem was O of h squared. If you want a very accuracy, you had to increase the order, but that's going to require many more computations, and even more than that, it's going to require that you have the derivatives, which is not usually the case. Now the proof is actually not that hard. I'm just going to have a sketch, and you should go over the proof by yourselves. If you notice, by definition, the truncation error, this is what we did at the beginning of the class, by definition is equals to this. This is the difference method. Okay. So this was the definition of local truncation error, which, remember, this is equals to this by the definition of the Taylor polynomials, Ci y of Ci, where Ci was between ti plus 1 and ti, and this was true for I equals to 0, 1, all the way to n minus 1. So this is the basis for the proof. The last part is not that hard, so you should all look to this in the book and convince yourselves. This is not going to be on the second test, but it will be on the third test. And this proof may actually be on the third test, so you should really check it out. Okay. Let me know if you have any questions, and that's it for section 5.3.